A silver ship vanishes into a swirling vortex of light, a cinematic trick we know all too well. But what if the universe's own rulebook contains a blueprint for a real time machine? Not with flashing consoles, but with pure, raw geometry. This is the promise of the Tipler cylinder, a theoretical construct born from the equations of Einstein himself. By the end of this journey, you will understand how a simple spinning cylinder could twist the fabric of reality into a loop, offering a passage to yesterday. We will confront the physics that might allow it and the monumental barriers that likely forbid it, exploring the razor's edge between profound discovery and pure fantasy. What does it truly mean for the past to be just another place we could visit? The blueprint for this cosmic gateway is deceptively simple in its description. A Tipler cylinder is in essence an object of pure theoretical extremes. Picture a rod, a perfect cylinder, stretching forever in both directions. This is not a piece of polished metal you could hold, but a structure of such immense density that its gravity warps the very universe around it. And it is not still. This infinite cylinder spins, rotating at a significant fraction of the speed of light. That combination, infinite length, impossible density, and near light speed rotation, is the recipe. It is not a machine with buttons and screens. It is a specific, severe curvature of spacetime itself, a valid solution to Albert Einstein's complex equations of general relativity. This means the math says such a shape could exist, and if it did, its influence on the fabric of reality would be profound. To a distant observer, it might appear as a shimmering, twisting spindle against the black of space, a cosmic drill bit boring not through rock but through time. The sheer scale is what defies imagination. We are talking about mass compressed to levels that make neutron stars look fluffy, and a length that has no end, a line drawn across the cosmos. This is the foundation of the idea, a geometric sculpture so extreme it bends the rules of cause and effect. The idea sprang not from science fiction, but from the pages of a physics journal. In 1974, a young physicist named Frank J. Tipler published a paper that would forever attach his name to this dizzying concept. Tipler was a mathematical physicist and cosmologist, a researcher deeply engaged with the most profound questions about the universe's structure and ultimate fate. His work often lived at the intersection of rigorous mathematics and speculative cosmology, a realm where you follow the equations wherever they lead, no matter how strange the destination. The cylinder we have been describing is formally known as a Tipler cylinder, or sometimes a Tipler time machine, a direct legacy of that groundbreaking work. It is important to understand that Tipler was not a fringe figure. He collaborated with and was respected by other notable scientists engaging with the biggest ideas in his field. What this highlights is a certain brand of scientific courage. Tipler was willing to take the established rules of general relativity, rules penned by Einstein, and push them to their absolute logical extreme. He asked, if the math permits a shape like this, what are the consequences? He was not necessarily advocating that we build one. Instead, he was mapping the outer boundaries of what is theoretically possible within our current understanding of gravity and spacetime. He was a cartographer of the impossible, drawing a blueprint for a region of physics where time itself becomes a road you can travel in both directions. This mindset is crucial. It separates wild fantasy from reasoned, if highly speculative, scientific exploration. The Tipler cylinder exists in that narrow space, a thought experiment forged from solid mathematics by a thinker who dared to ask what happens if we take our best theories to their breaking point. But to truly grasp how a spinning cylinder could become a time machine, we need to understand the universe's canvas. Albert Einstein's theory of general relativity forever changed our picture of gravity. Before Einstein, we thought of gravity as a force, a mysterious pull between objects like the Earth tugging on the Moon. Einstein's revelation was far more elegant. He proposed that what we perceive as gravity is not a force at all, but a consequence of geometry. Think of the fabric of the universe as a vast, stretchy trampoline mat. This mat is spacetime itself, a single entity blending the three dimensions of space with the one dimension of time. Now, place a heavy object like a bowling ball in the center of that trampoline. The ball creates a deep dip, a curve in the mat. If you then roll a marble nearby, it will spiral inward toward the bowling ball, not because the ball is magically pulling it, but because it is simply following the curved surface. The marble is taking the straightest possible path along a bent landscape. That is gravity. Mass and energy, like the bowling ball, tell spacetime how to curve. And curved spacetime tells objects like the marble how to move. The Earth orbits the Sun because it is rolling around the Sun's massive dimple in the cosmic fabric. This is the core idea. Gravity is geometry. Now enter the Tipler cylinder. It is not a machine that generates a new force. It is a very specific, very extreme shape carved into that spacetime trampoline. The cylinder's immense mass and rapid spin do not just create a simple dip. They twist the fabric, creating a kind of whirlpool or vortex in the geometry of reality itself. The cylinder's rotation literally drags spacetime around with it, like a spoon stirring a thick fluid. And within this twisted region, the paths that objects can take, the so-called straight lines or geodesics, can loop back on themselves in time. The Tipler cylinder, therefore, is a direct prediction of this geometric view of the universe. If general relativity is the rulebook, the cylinder is one of the strangest plays the rules seem to allow, a configuration of mass and motion that bends the trampoline mat into a closed loop where the end connects back to the beginning. This twisting effect has a name, a phenomenon predicted by Einstein's equations and confirmed by our own satellites. It is called frame dragging or the lens-stirring effect. To understand its power, picture a spoon slowly stirring a vat of thick golden honey. As the spoon rotates, it does not just move through the honey. It pulls the honey around with it, creating a gentle swirl that extends far beyond the spoon itself. In our universe, spacetime is that honey, and any rotating mass is that spoon. The Earth, as it spins, ever so slightly drags the fabric of spacetime around with it. This is not a metaphor. Sensitive instruments aboard Gravity Probe B have measured this minute drag around our planet. It is a real physical effect, a testament to the fact that space and time are a malleable medium. Now amplify that effect beyond all reason. Replace the Earth with our infinite, hyper-dense cylinder spinning at a blistering pace. The gentle swirl becomes a cosmic maelstrom. The cylinder does not just drag space around it, it drags time. This is the profound leap. In the whirlpool surrounding the cylinder, the flow of time itself is pulled into a circular current. Clocks closer to the surface of the cylinder would tick at a different rate than those farther away, not just due to gravity, but due to this rotational drag. The fabric becomes so twisted that the lines marking before and after begin to curl. Within a certain region around this monstrous spindle, the twisted paths through spacetime, the geodesics, could theoretically form closed timelike curves. This is the technical term for a path that loops back to its own starting point in time. An object following such a path would not be traveling faster than light. It would simply be riding the contoured landscape of reality, like a marble rolling along a twisted track that eventually brings it back to where it began, only earlier. The cylinder's rotation warps the timeline into a literal loop. One moment you are in its future, following the curve, and the next you find yourself in its past, having never broken the cosmic speed limit. The machine is the geometry, and the key that turns the lock is this relentless, universe-bending spin. This looping path is what physicists call a closed timelike curve. The name sounds complex, but the idea is hauntingly simple. In our everyday experience, time is a one-way street. You are born, you grow, you move forward along your personal timeline, your world line. A closed timelike curve is a world line that does not just go forward. It bends, it twists, and eventually it curves all the way back to meet itself. It is a road that starts at your front door, wins through the years, and then deposits you back on your own doorstep, only at a moment before you ever left. You have traveled into the future only to circle back into your own past. This is not breaking the laws of physics as we know them. Within the twisted geometry around something like a Tipler cylinder, such a path could be the straightest possible line an object could follow. It is simply riding the contours of a profoundly warped reality. Think of it like this. On a flat piece of paper, the shortest path between 2 points is a straight line. But if you take that paper and curl it into a cylinder, taping the ends together, a new possibility emerges. You can draw a line that goes around the cylinder and meets its own beginning. That line is closed, a loop. In the warped spacetime near the cylinder, time itself becomes like that curled dimension. A closed time-like curve is the loop you can walk, a journey where your destination is your own point of departure, just at an earlier hour on the cosmic clock. This is the mathematical core of the entire concept. The cylinder does not teleport you. It reshapes the landscape so thoroughly that a journey through time becomes as geometrically possible as walking in a circle around a tree. That infinite length is not a suggestion, it is an absolute mandate. For the closed time-like curve to form, for the loop in time to seal itself shut, the cylinder cannot simply be very long. It must have no end, stretching forever in both directions. This is where the beautiful theory collides head-on with a brutal, physical impossibility. A finite cylinder, no matter how dense or how fast it spins, simply will not produce the necessary spacetime geometry. The mathematics is clear. The twist it creates in the fabric of reality would be incomplete, like a whirlpool that suddenly hits a wall. The closed paths through time would be severed, broken off before they could circle back on themselves. You would get a region of incredibly warped space, perhaps, but no stable, traversable loop into the past. The infinite length is what allows the gravitational and rotational effects to propagate in a perfectly uniform, unchanging manner along the entire structure. It creates a symmetry that the equations demand, a clean, endless curve in spacetime that can smoothly connect future to past without any messy edges or boundaries to disrupt the loop. Without that infinity, the time machine falls apart at the very first step, and this requirement, more than any other, is what exiles the Tipler cylinder from our engineering dreams and confines it to the pages of theoretical physics. We are creatures of a finite universe. We build finite things from finite materials. The concept of constructing an object that literally never ends is, for all practical purposes, meaningless. It is not an engineering challenge on a grand scale. It is a logical paradox made solid. How would you even begin? Where would the material come from? How would you ensure its perfect density and rotation over a distance that has no end? The infinite cylinder is a ghost in the machine of general relativity, a shape that the math permits but reality almost certainly forbids. It transforms the idea from a potential technology into a profound philosophical tool, a way to test the absolute limits of our best theory of gravity by asking what happens when we push its parameters to an unreal extreme. Even if we could somehow build an infinite cylinder, its own weight would crush it instantly. The gravitational forces within an object of such impossible density would be catastrophic, causing it to collapse inward into a black hole or simply tear itself apart. This introduces a second, even stranger requirement for our theoretical time machine, a kind of cosmic scaffolding to hold it up. Physicists call it exotic matter. This is not just a new element on the periodic table. Exotic matter is a hypothetical substance that possesses a property so bizarre it seems to defy common sense: negative energy density. To understand this, think of the vacuum of space. We often call it empty, but quantum physics tells us it is seething with fleeting particles and fields, a roiling sea of potential. This vacuum has a baseline energy, often considered zero for simplicity. Exotic matter would have less energy than that. Its energy density would be negative, meaning it would exhibit a kind of gravitational repulsion. Instead of pulling things together like normal matter, it would push them apart. This anti-gravity effect is precisely what some mathematical models suggest would be needed to line the interior of a Tipler cylinder, to provide an outward pressure strong enough to counteract the immense inward crush of its own gravity. It would be the ultimate support structure, an invisible force field woven from the fabric of quantum theory itself, keeping the cylinder from imploding into oblivion before it could ever twist time. The most promising candidate for this exotic matter comes from a real, measurable quantum effect, the Casimir force. In a simplified view, if you take two perfectly smooth, uncharged metal plates and place them extremely close together in a vacuum, they will be pushed toward each other by an invisible force. This happens because the space between the plates restricts the kinds of quantum fluctuations that can exist there, creating a subtle pressure difference. The energy density in that narrow gap is technically lower than the energy density of the surrounding vacuum. In a very specific, localized sense, this region has a form of negative energy density. It is a tiny, laboratory-scale hint that the concept might not be pure fantasy. But the leap from this microscopic Casimir effect to the astronomical quantities needed to stabilize an infinite cylinder is unimaginably vast. We are talking about bottling a ghostly quantum whisper and amplifying it into a cosmic shout loud enough to hold back a star's worth of gravity. The existence of such bulk, stable, usable exotic matter remains entirely speculative, a phantom in the equations. So now our time machine requires not one but two physical impossibilities, an object of infinite length and a material that defies the very pull of gravity. Each layer deepens the mystery, transforming the cylinder from a mere machine into a question about the deepest, most counterintuitive rules of reality itself. Gravity would be our first and most formidable foreman on this project. To even begin shaping spacetime into a time loop, we would need to assemble a staggering amount of mass. We are not talking about the weight of a planet or even a sun. The most conservative estimates suggest we would need to compress the equivalent of several neutron stars into our cylindrical form. A single neutron star, the remnant core of a giant star, packs about 1.4 times the mass of our entire sun into a sphere barely the size of a city. Our blueprint calls for multiple instances of that density, but stretched into a line. So step 1, locate and carefully disassemble not one, but several of these cosmic powerhouses, each one a boiling cauldron of degenerate matter held together by the strongest force we know. The energy required for such stellar demolition and transport is beyond any civilization's ledger. Once we have our mountain of star stuff, the real compression begins. We must forge it into the shape of a perfect cylinder, a rod with a smooth, unblemished surface. This is not like rolling clay. We are dealing with matter under pressures that make the core of a planet feel like a soft pillow. The forces involved would naturally want to crush this cylinder into a sphere, or worse, a black hole. To prevent that, we would need to apply unimaginable containment fields, perhaps harnessing the very fabric of spacetime to act as a mold, shepherding this impossible density into its required form. The cylinder cannot waver or bulge. Its surface must be flawless, its density perfectly uniform from end to end, a monument to precision on a scale that mocks our finest engineering. Then we must set it spinning, not a gentle rotation but a furious whirl approaching a significant fraction of the speed of light. We are not turning a key here. We are imparting angular momentum to an object with the mass of dead suns. The energy input would be astronomical, a sustained torrent of power that could light galaxies. This spin is the stirrer that twists the honey of spacetime, too slow, and the frame dragging is a gentle ripple, not a vortex, too fast, and the centrifugal forces might overcome our containment, flinging our carefully gathered mass back into the void. The balancing act is terrifying, a dance on the edge of gravitational collapse and relativistic disintegration. And finally, we face the ultimate laughable instruction. Extend it. The cylinder must not just be long, it must have no end. The construction manual would simply read, "Continue the cylinder indefinitely in both directions." There is no final weld, no capstone ceremony. The project is, by its very definition, never finished. You would be building a structure that stretches beyond the horizon of the observable universe, a line drawn in super-dense matter that has no terminus. It makes building a Dyson sphere around a star seem like a weekend craft project. This requirement alone transforms the entire endeavor from an engineering challenge into a philosophical punchline, a cosmic joke written in the language of general relativity. The scale is so absurd it circles back to being profound, teaching us less about how to build a time machine and more about the breathtaking, often bizarre, limits of the physical laws we think we understand. So you stand before the impossible machine, its infinite form humming with twisted gravity. How would you actually step into yesterday? The journey is not a sudden leap, but a careful navigation along the contours of warped reality. Your vessel, a ship built to withstand tidal forces that could shred planets, would not fly toward the cylinder. Instead, it must match the cylinder's furious spin, entering a precise, spiraling dance around its shimmering surface. Think of it as threading a cosmic needle along a corkscrew path through time itself. You would not point your ship at a date on a calendar. You would plot a trajectory, a specific geodesic in the twisted spacetime around the spindle, a road that exists only because the cylinder carved it into the universe. Your engines fire not for a burst of speed, but for perfect control, nudging you onto this invisible, spiraling track. As you begin your first loop, the effect is subtle. The stars outside your viewport smear into strange, circular streaks, not from your speed, but from the frame dragging of spacetime itself being whipped around the cylinder. Time for you continues to flow forward normally inside your ship, but relative to the rest of the universe, something profound is happening. With each complete orbit you make around the cylinder, you are not just moving through space. You are moving backward along the cylinder's own timeline. The mathematics suggests that one full, stable orbit could translate to a journey a few hours or perhaps days into the past. To travel further back, you would need to complete more loops, spiraling closer to the cylinder's surface with each revolution, following a helical path that winds deeper into the vortex. It is a gradual, deliberate process. 10 orbits might take you back a week, 100 orbits years, 1,000 centuries. You are essentially winding the clock back by tracing circles in a gravity well where time itself is coiled like a spring. The cylinder acts as a temporal spindle, and your ship is the thread weaving backward through the fabric of moments, but the journey is only half the puzzle. Arrival requires an equally precise exit. You cannot simply stop your ship and find yourself in ancient Rome. You must disengage from the spiral at an exact mathematical point, a specific location in both space and in the twisted timeline. Your navigational computers, calculating in the language of curved geometry, would find the moment where your world line, the path of your own personal time, intersects with the historical moment you wish to visit. At that precise coordinate, you fire thrusters to break the spiral, pushing away from the cylinder's influence and back into the normal, flat flow of universal time. It is a leap from a twisting river back onto a still lake. One moment you are in the roaring temporal vortex, and the next you are adrift in the quiet of space. But the stars have shifted. The light from distant galaxies is older or younger than it should be. Your instruments confirm it. You have not moved in space, not in any conventional sense. You have simply stepped off the carousel at a different point in its rotation, and in doing so, you have been deposited into an earlier chapter of the universe's story. The cylinder itself remains eternally spinning, a silent loom upon which timelines can be woven and unwoven. This seamless journey into yesterday raises a chilling question. What if you used this power to erase the very reason for your journey? This is the grandfather paradox, the classic logical trap at the heart of all time travel stories. You travel back in time, meet your grandfather before he has children, and accidentally cause his death. If he dies young, your parent is never born. If your parent is never born, you are never born. But if you are never born, you could not have traveled back to kill him. The paradox creates a loop of impossible cause and effect, a logical knot that seems to unravel the very possibility of changing the past. The existence of a device like the Tipler cylinder forces physics to stare this paradox directly in the face and propose answers. One compelling solution comes from a Russian physicist named Igor Dmitrievich Novikov. He proposed the self-consistency principle, a rule for the universe that is as elegant as it is restrictive. It states that any actions taken by a time traveler were always part of history. The past is not a blank slate to be rewritten. It is a finished book, and your journey back is simply a paragraph that was always there. In this view, you could certainly travel back and meet your grandfather. You might even try to cause his death, but the principle insists that some subtle twist of fate, would always prevent you from succeeding. Your gun would jam, you would slip on a banana peel at the crucial moment, a sudden noise would distract you. The universe conspires through countless tiny coincidences to ensure that all events remain consistent. You cannot change the past because you already didn't. Your presence there is just another thread in the tapestry woven in from the beginning. The past is fixed, immutable, and paradox-free. Your free will still exists, but your choices are channeled along the one single, consistent timeline that already includes your journey. It is a universe with no room for mistakes, only for revelations about what always was. There is another, wildly different answer that comes from quantum theory. This is the many worlds interpretation. Here, every possible outcome of every quantum event actually happens, but in a newly branching parallel universe. Apply this to time travel and the paradox evaporates. When you travel back and intervene in the past, you are not changing your original timeline. Instead, the moment you arrive or the moment you take an action that alters events, the universe splits. You create a new, separate branch of reality. In one branch, your grandfather lives and your original history remains intact, safe and unchanged. In the new branch you now inhabit, your grandfather dies and a future unfolds where you were never born. This new timeline exists independently, a parallel track running alongside the old one. You have not erased yourself, you have simply stepped into a reality where a different version of you never existed. The Tipler cylinder in this model would not be a shuttle to your own past, but a gateway to the past of an infinite array of nearly identical worlds. Each journey could spawn a new branch, a new variation on history. This transforms time travel from an editing of a single story into an exploration of a limitless library of alternate histories. Both ideas, consistency and branching worlds, are attempts to rescue logic from paradox. They represent two fundamental philosophies about the nature of reality. Is the universe a single, deterministic story where everything is pre-written, or is it a perpetually splitting tree of endless possibilities? The Tipler cylinder, a mere twist in space-time, becomes a lens that magnifies these deepest of cosmic questions, challenging not just what we can build, but what we believe about the very structure of existence. While the Tipler cylinder relies on a monumental application of known physics, other blueprints for time travel require us to rewrite the rulebook entirely. Consider the wormhole, perhaps the most famous time machine concept in popular science. An Einstein-Rosen bridge, as it is formally known, is not a tunnel bored through space but a shortcut. Picture the universe as a vast sheet of paper. If you want to travel from one point to another far away, you must traverse the entire distance across the sheet. But if you could fold the paper, bringing those 2 points to touch, you could punch a hole straight through, creating a bridge. That is a wormhole, a theoretical connection between two distant regions of spacetime. To make it a time machine, you would need to manipulate one of its mouths. If you could take one end of the wormhole and accelerate it to near light speed and then bring it back, time dilation from Einstein's special relativity would kick in. Less time would pass for the accelerated end. So, if you step into the stationary end in the year 2100, you might exit the accelerated end in the year 2050. You have traveled into the past relative to your starting point. The mechanism here is fundamentally different from the Tipler cylinder. The cylinder warps time by creating a whirlpool in spacetime through sheer mass and spin. The wormhole uses the differential flow of time between two connected points, but the challenges are just as immense. Keeping a wormhole stable and open wide enough for anything to pass through is believed to require the same exotic matter with negative energy density that the Tipler cylinder needs, and in similarly vast quantities. Furthermore, many physicists suspect that stabilizing a wormhole would demand a theory of quantum gravity, a unified framework that merges general relativity with quantum mechanics, something we do not yet possess. Then there are cosmic strings. These are not science fiction either, but hypothetical, incredibly thin defects in the fabric of the universe, relics from its earliest, most violent moments of expansion. Think of them as cracks frozen into the structure of reality itself, thinner than an atom but stretching across the entire cosmos and possessing unimaginable density. A single cosmic string could have the mass of an entire mountain range compressed into every centimeter of its length. Here is where it gets interesting for time travel. Two such cosmic strings moving past each other at near light speed in a precise parallel configuration could theoretically warp spacetime between them enough to create closed time-like curves. The mechanism is closer to the Tipler cylinder, using the immense gravitational field of ultra-dense objects in motion to twist spacetime. However, cosmic strings are even more speculative. We have no confirmed evidence they exist, and if they do, finding two, moving them, and aligning them perfectly is a task of literally cosmic proportions. This comparison reveals a crucial distinction. The Tipler cylinder, for all its absurd requirements, operates purely within the domain of classical general relativity. It is a thought experiment that pushes Einstein's equations to their extreme, but it does not inherently demand new physics. Wormholes, by contrast, seem to require a handshake between the very large and the very small, a theory of quantum gravity, to become more than a mathematical curiosity. In this sense, the cylinder is a purist time machine, a monster built from the known bricks of gravity and motion, even if those bricks are impossibly heavy and infinitely long. It asks, what is the ultimate consequence of this theory we already have? The wormhole asks, what new theory must we discover to make this possible? One is an exploration of limits, the other a promise of a future physics. Both highlight that the path to yesterday is not a single road, but a maze of theoretical possibilities, each with its own universe of problems to solve. Yet these cosmic blueprints face a far deeper challenge than mere engineering. The true barrier may not be a lack of materials, but a fundamental war between the universe's two greatest theories. On one side stands general relativity, the majestic description of gravity and spacetime that generously permits closed time-like curves within twisted geometries like the Tipler cylinder. On the other stands quantum mechanics, the wildly successful rulebook for the subatomic world, governing particles, forces, and probabilities. These two titans describe reality with stunning accuracy, but they speak entirely different languages, and on certain points they violently disagree. Where general relativity sees a smooth, geometric fabric, quantum mechanics sees a frenetic, probabilistic foam. When these two visions are forced to meet in the extreme conditions of a time machine, the result is not a blueprint but a battlefield. The conflict centers on a strange quantum phenomenon known as vacuum fluctuations. Even in what we call empty space, the quantum vacuum is never truly empty. It is a seething sea of potential where pairs of virtual particles and antiparticles constantly wink into and out of existence, borrowing energy from the universe for an immeasurably brief moment before annihilating each other. This is not just theory. We can measure the subtle effects of this quantum activity. In the calm, flat spacetime of our everyday universe, these fluctuations are a gentle background hum. But introduce a closed timelike curve, a loop where an object can return to its own past, and this gentle hum becomes a deafening, destructive scream. The mathematics suggests that these quantum fluctuations would travel around the time loop, not once, but an infinite number of times. With each pass, the energy of the fluctuation would build upon itself, amplifying without limit. The vacuum energy would skyrocket to infinity, creating a catastrophic feedback loop of pure energy that would either destroy the time loop itself or collapse it into a singularity long before any traveler could ever use it. It is as if nature has a built-in fuse, and the moment you try to wire time into a circuit, that fuse blows. This terrifying prospect led the legendary physicist Stephen Hawking to propose a profound idea, the chronology protection conjecture. Hawking, who deeply understood the clash between these two theories, essentially argued that the universe must have a law against time travel to the past. He suggested that whenever the conditions for a closed timelike curve begin to form, whether around a Tipler cylinder, a wormhole, or cosmic strings, quantum effects will always intervene to prevent it. The vacuum fluctuations, or some other quantum process we do not yet fully understand, would act as nature's ultimate censor, a cosmic editor that crosses out any plotline containing a paradox before it can be written. Hawking famously stated that the absence of tourists from the future is perhaps the strongest evidence for his conjecture. If time machines were possible, even in principle, wouldn't our history be filled with visitors? His idea is not a proven theorem, but a powerful hypothesis born from the glaring incompatibility between our two best descriptions of reality. It posits that the universe is not just physically hostile to time machines, but logically self-protecting. The laws of quantum physics, in this view, are the guardians of causality, ensuring that cause always precedes effect, that history remains a single, consistent story, and that the grandfather paradox is not just a logical puzzle, but a physical impossibility enforced by the very fabric of existence. The Tipler cylinder, then, becomes more than a test of general relativity. It becomes a litmus test for the ultimate unification of physics. To build one, we would not just need infinite mass and exotic matter. We would need to reconcile the two titans, to find a theory of quantum gravity that tells us what truly happens when the smooth geometry of spacetime is bent into a loop at the quantum scale. Until that day, Hawking's cosmic censor stands watch, ensuring that yesterday remains forever, a place we can remember but never revisit. Frank Tipler's journey did not end with infinite cylinders and closed time loops. In a fascinating and controversial pivot, the physicist who once mapped the edges of general relativity turned his formidable mind toward an even more profound frontier, the ultimate fate of the cosmos and its potential intersection with the divine. In the 1990s, Tipler co-authored a book titled The Physics of Immortality, followed later by The Physics of Christianity. These works represented a dramatic shift from the clean, if extreme, mathematics of relativity to a grand, speculative synthesis of cosmology, computer science, and theology. Tipler proposed what he called the omega point theory, a vision where the far future evolution of the universe, driven by intelligent life, becomes functionally indistinguishable from God. In this model, a future civilization of unimaginable power would use the entire cosmos as a computational substrate to resurrect every consciousness that ever lived through perfect simulation, achieving a form of eternal life. This was not a religious text in the traditional sense, but a radical attempt to frame theological concepts like resurrection, the soul, and God within the language of physics and information theory. To many of his peers, this was a bridge too far, a leap from rigorous theoretical physics into untestable metaphysical speculation. His work was met with significant criticism from the scientific community, who argued it misapplied scientific concepts and ventured far beyond empirical evidence. Yet, this evolution in Tipler's thinking is deeply revealing. It showcases a mind relentlessly pursuing the biggest possible questions, regardless of disciplinary boundaries. The same intellectual courage that led him to take Einstein's equations to their logical extreme with the cylinder, to ask what the math truly permits no matter how strange, later compelled him to ask what the ultimate implications of cosmology and information might be for the human condition. The Tipler cylinder was a question about the geometry of reality. The omega point was a question about its purpose and end. Both are products of a thinker who refused to let the possible be limited by the practical, who saw physics not just as a tool for prediction, but as a framework for exploring the deepest mysteries of existence, from the twisting of time to the nature of consciousness itself. His career arc reminds us that at the furthest edges of theoretical science, the line between profound insight and profound speculation can become very thin, and the quest for understanding can lead to territories that challenge not just our equations, but our very conception of reality and our place within it. The infinite cylinder may live in the realm of theory, but its shadow stretches far across our stories. While its precise mathematical name rarely appears on screen, the concept of a gravity-twisting, spinning structure as a time machine has become a staple of serious science fiction, a trope for writers who want their fantastical journeys to feel grounded in real physics. Perhaps the most famous and direct homage appears in the film adaptation of Carl Sagan's novel Contact. In the story's climax, the protagonist, Dr. Ellie Arroway, is propelled through a series of wormholes via an elaborate machine. The machine's design is not a sleek starship, but a vast, complex structure of spinning rings. This visual and conceptual blueprint was directly inspired by theoretical work on wormholes and closed timelike curves, drawing from the same well of ideas that produced the Tipler cylinder. It is hard science fiction's attempt to visualize the unseeable, to give form to the equations of Kip Thorne, the physicist who consulted on the film. The spinning rings serve as a narrative bridge, translating dense theory into a cinematic experience of wonder, suggesting that the universe's greatest secrets might be unlocked not by magic, but by machinery that obeys its deepest laws. A more haunting and abstract interpretation permeates the cult classic Donnie Darko. The film's central enigma is a mysterious, apocalyptic tangent universe, and its harbinger is a sinister, liquid-like spear of energy that pierces Donnie's chest. This manifestation, often described as an artifactual vortex, bears a conceptual resemblance to the twisted spacetime around a rotating mass. While not a cylinder, it functions as a conduit that warps time and destiny, pulling Donnie into a predetermined path. The film delves into the philosophy of predestination and closed time-like curves, asking what happens when you glimpse the machinery of fate. Donnie's journey is less about controlling time and more about understanding his role within a fixed, looped reality, echoing the self-consistency principle that would govern a real Tipler cylinder's use. It is a psychological and philosophical exploration of the cylinder's core implication, that time might be a closed loop we are powerless to break. Beyond the screen, the cylinder and its conceptual siblings have fueled countless novels and video games, providing a bedrock of plausibility for epic narratives. Author Stephen Baxter, known for his rigorously researched science fiction, has employed Tipler cylinders and cosmic strings as plot devices to enable human expansion across eons. In the world of video games, the premise often shifts from observation to interaction. Titles like the Portal series, with their handheld devices that warp spatial geometry, play with the foundational idea that reality can be folded. More directly, games with time manipulation mechanics, where players rewind events or create temporal duplicates, are engaging with the personal consequences of closed time-like curves on a human scale. These narratives rarely stop to explain the field equations. Instead, they borrow the conceptual weight, the sense that this is not mere fantasy, but a future technology waiting at the furthest edge of human understanding. The cylinder becomes a symbol, a stand-in for the ultimate ambition of science, to not just understand the universe, but to reshape its most fundamental properties, to turn the fabric of existence into a tool. This recurring presence in our fiction serves a vital purpose. It transforms an abstruse mathematical possibility into a shared cultural touchstone. When we watch a character enter a spinning ring of light, we are not just seeing a special effect. We are witnessing a century-old conversation between imagination and mathematics, a dialogue that began with Einstein's pen and continues in writers' rooms and game studios. The Tipler cylinder, in all its infinite, impossible glory, represents a specific brand of hope, the hope that the universe is not just strange but engineerable. That the laws of physics, no matter how daunting, are a blueprint, not a prison. And while we may never forge a cylinder from dead stars by dreaming of it, by writing it into our stories, we keep that hope alive, exploring the consequences of time travel from the safety of a thought experiment that continues to bend our minds, if not our reality. The power to visit yesterday is not just a question of physics, but of conscience. Who would hold the key to such a door? The very notion shatters our assumptions about justice, history, and human agency. Imagine a world where a Tipler cylinder or its equivalent exists, a single, monumental structure twisting in the void. Control over it would instantly become the ultimate geopolitical prize, a source of power eclipsing every nuclear arsenal and economic empire combined. It would not be a technology for public use. It would be a state secret of unimaginable magnitude, guarded with a paranoia that makes Cold War secrecy look quaint. Access would be rationed, debated by councils of scientists, historians, and ethicists, each journey requiring a justification that balances immense cost against potential world-altering consequence. The moral responsibility would be paralyzing. Do you send an observer to witness the Library of Alexandria before the fire, to passively record knowledge otherwise lost? The historian in us screams yes, but the physicist warns that even observation is an intervention. Your ship's mass, your heat signature, a single microbe escaping a filter, these are physical interactions with the past. In a universe governed by the self-consistency principle, your mere presence was always part of that fire's cause. In a many worlds branching reality, your act of witnessing creates a new timeline where your shadow falls across history. There is no purely passive observation. To be there is to change it in ways subtle or profound. This leads to the darkest temptation, the urge not to witness but to correct. What government, what individual could resist the pull to prevent a tragedy, to avert an assassination, to stop a plague, to whisper a warning into the right ear? The moral calculus seems clear: to save millions, but history is a fragile, interconnected web. The second-order consequences are utterly unknowable. Preventing a single war might stifle the technological innovation or social unity that conflict spurred. Stopping a pandemic might lead to overpopulation and a different, greater collapse decades later. The well-intentioned traveler becomes a god with no wisdom, editing a story they cannot possibly comprehend in its entirety, and this assumes the best of intentions. The potential for tyranny is absolute. A regime could cement its power forever by eliminating its past rivals before they were born. It could plunder historical treasures, not for a museum, but for a private vault. It could rewrite its own foundational myths, not with propaganda, but with literal, physical evidence planted in the archaeological record. The time machine becomes the ultimate weapon of control, erasing not just the future of an enemy, but their entire lineage from history itself. These terrifying scenarios force us to confront the oldest philosophical debate in a new, stark light: determinism versus free will. If closed time-like curves are possible and the self-consistency principle holds, then our universe is a block where every event is fixed. Your journey to the past was always part of the timeline. Your choice to go was the only choice you could ever have made. Free will becomes an illusion, a feeling we have as we travel along a rail that was welded shut at the dawn of time. The past is not a place you change, it is a place you fulfill. This is a profoundly unsettling vision, reducing all human struggle, love, and triumph to a pre-recorded script. Yet, if the many worlds interpretation is correct, free will erupts with a vengeance. Every decision at a temporal crossroads spawns a new universe. Your choice to intervene creates a branch where you are a hero, and another where you are a monster, and another where you never arrived at all. Your will is real, its consequences are infinite, and the weight of that responsibility is infinite as well. You are not following a script, you are an author, but you are writing in a library that instantly creates a new copy of reality with every pen stroke. Neither answer is comfortable. One makes us passengers in a story with no alternative. The other makes us reckless gods in a multiverse we cannot hope to navigate. The Tipler cylinder, therefore, is more than an engineering puzzle. It is a mirror. It reflects back our deepest fears about power, our anxiety over our place in the cosmos, and our agonizing uncertainty about whether our choices are truly our own. To build a time machine would be to finally answer these questions, not with philosophy but with experience, and that may be the most frightening outcome of all. So we must ask, what would we actually do with such a key? The most obvious and trivial answer is tourism. A thriving, impossible industry would bloom, offering curated trips to witness the dinosaurs, to walk the streets of ancient Rome, or to hear the first performance of a lost symphony. But this is a child's dream, a postcard from a paradox. The real applications, if such a machine could ever be tamed, would be far more profound and unsettling. Science would undergo a revolution. History would cease to be a discipline of fragments and become a laboratory. Imagine sending a probe, a silent, microscopic observer, to the moment just before the extinction of the dinosaurs. We could finally settle the debate, watching in real time as an asteroid carved its fiery path through the atmosphere, measuring the exact impact, the global climate shock, the slow, terrible collapse of an era. We could witness the formation of the solar system from a front row seat, collecting pristine samples of the primordial cloud. Cosmology would become an experimental science. We could test our theories about the early universe by simply going back and taking a look, verifying the inflationary epoch or the first fusion in the earliest stars. The ultimate cold case files would be solved not by deduction but by direct observation. The fate of lost civilizations, the true authorship of disputed works, the precise moments of great discoveries all laid bare. Knowledge itself could be preserved against any catastrophe. A time capsule would no longer be a hopeful box buried in the ground, but a literal pipeline to the future. A society facing collapse could encode its entire cultural and scientific database and send it spiraling backward to a point before the disaster, a message to its own past self, a loop of wisdom designed to break the cycle of its own downfall. This loops into the most staggering possibility of all, cosmic engineering on a scale that mocks human lifetimes. A civilization could use the cylinder as a strategic tool for projects that span millions of years. Need to move a star, plot a course that uses the time loops to allow a small fleet to make an infinite number of gravitational nudges, appearing to complete the work from the outside in a single century. Want to assemble a Dyson sphere? Dispatch constructor drones that use the cylinder to revisit the construction site era after era, each visit adding another layer, another panel, their cumulative work across eons appearing to an external observer as a sudden, miraculous feat. The cylinder becomes a temporal multiplier, a way to leverage a single moment of effort across the breadth of history. Of course, this is all a delightful fantasy, a castle built on the twin impossibilities of infinite length and exotic matter. Yet, as a thought experiment, it forces a valuable perspective. It asks us what we would value if the entire timeline were our workshop. Would we be historians or voyeurs? Scientists or gods, preservers or meddlers? The uses we dream of reveal our own priorities, our hunger for truth, our fear of loss, and our boundless ambition to leave a mark not just on the world but on time itself. The Tipler cylinder, in the end, is less a machine and more a question. What would you do with all of yesterday? But if building one is beyond our reach, could the universe have forged its own time machines? The search for natural Tipler cylinders takes us to the universe's most violent and creative epoch, the first fractions of a second after the Big Bang. During this primordial chaos, the fabric of spacetime itself was undergoing unimaginable stresses and phase transitions. It is within this forge that physicists speculate the seeds of such structures could have been planted. One compelling idea is that they might have formed as topological defects, similar to cosmic strings, but in a cylindrical configuration. As the hot, dense universe expanded and cooled, the underlying fields governing forces and particles might have settled into their stable states unevenly, like a cooling sheet of glass developing cracks. In rare regions, these cracks could have taken the form of infinitely long, rotating cylinders of trapped energy, frozen into the expanding cosmos. They would be relics, fossils from the moment physics itself was taking shape. Another possibility ties them to cosmic inflation, that brief period of hyper-accelerated expansion thought to have smoothed and shaped our universe. The immense energies at play during inflation could have stretched quantum fluctuations into macroscopic structures, potentially including the precursors to these exotic objects. If they formed, they would be among the most bizarre and ancient artifacts in existence, spinning silently in the darkness since before the first stars ignited. So why haven't we found one? Astronomers have looked, or at least they have looked for the signatures such a monster would inevitably leave on the cosmos. A natural Tipler cylinder, with its infinite length and immense density, would be a gravitational lighthouse of staggering power. It would warp the path of light from galaxies behind it, creating distinctive, telltale arcs and multiple images in a pattern unlike any gravitational lens produced by a star or black hole. Its furious rotation would generate a continuous storm of gravitational waves, ripples in spacetime with a very specific, steady frequency, like a constant, low hum woven into the cosmic background. Our observatories, like LIGO and Virgo, listen for the chirps of colliding black holes, but they are also sensitive to such persistent signals. No such continuous hum has been detected. Furthermore, the cylinder's gravitational drag on nearby stars and gas would create anomalous, swirling motions that would stand out in galactic surveys. We see nothing that matches. The absence of evidence is telling. It suggests that if the conditions to create a Tipler cylinder ever existed in the early universe, they were either extraordinarily rare or, more likely, physically forbidden from becoming stable. The same quantum effects that may enforce chronology protection could have prevented these defects from ever settling into a time-twisting configuration, causing them to decay or collapse instantly. Their theoretical status is thus reinforced not just by our inability to build them, but by the universe's apparent silence on the matter. The cosmos, it seems, has not left any blueprints for time machines lying around. They remain where Frank Tipler first placed them, in the elegant, severe landscape of pure mathematics, a reminder that some doors in the mansion of reality are locked not by our ignorance, but by the very laws that hold the walls upright. The universe's silence on natural time machines speaks volumes, but the theoretical objections are even louder. Within the physics community, the Tipler cylinder is often met with a mixture of intellectual respect and practical dismissal. The criticisms are not about the mathematics, which is sound, but about the leap from equation to existence. The two core requirements, infinite length and exotic matter, are widely seen as insurmountable physical impossibilities, deal breakers that relegate the concept to the realm of pure thought. An object of infinite length is not just difficult to build, it is a logical contradiction within a finite, observable cosmos. As for exotic matter with stable, macroscopic negative energy density, most physicists argue it simply does not exist in the form or quantity required. It is one thing to measure the Casimir effect in a lab, and another to harvest enough of this phantom material to line a structure light years long. These are not engineering hurdles, they are violations of what we believe to be fundamental constraints of reality. Many prominent theorists view the cylinder not as a blueprint but as a mathematical curiosity. Kip Thorne, who deeply explored wormholes, has expressed skepticism about the physical plausibility of such constructs, emphasizing the profound instability introduced by quantum effects. Others see it as a kind of stress test for general relativity, a solution that exists on paper but that the universe actively prohibits through other, deeper laws. The cylinder, in this view, is less a machine and more a warning sign, a red line drawn by physics itself. It shows where the elegant geometry of Einstein's theory, if taken too literally without the counterbalance of quantum mechanics, leads to conclusions that are logically coherent but physically absurd. This pushback is not a dismissal of Tipler's work, but a crucial part of the scientific process. It forces a vital distinction between what is mathematically allowed and what is physically possible. The cylinder lies in that narrow, fascinating gap. It remains an exceptionally useful tool, not for building time machines, but for probing the absolute outer limits of general relativity. By pushing the theory to its breaking point, it helps us understand where it fails and where a new, unified theory of quantum gravity must take over. It is a lighthouse at the edge of known physics, and its most important function is to illuminate the rocky, uncertain shores beyond. This relentless pursuit of the impossible is not a scientific dead end. It is the engine of discovery. Why spend a moment on a machine we can never build? Because the Tipler cylinder and ideas like it are not blueprints for workshops. They are probes sent into the dark corners of our theories, revealing cracks in the foundation we never knew were there. When we take a beautiful, powerful theory like general relativity and push it to an extreme, we force it to confess its secrets and its shortcomings. The infinite length requirement is not just an absurdity, it is a glaring signpost that says, here, something is missing. It tells us that general relativity on its own cannot handle a finite time machine without breaking, pushing us to ask what new physics, perhaps a theory of quantum gravity, must step in to take over. The need for exotic matter forces us to confront the strange, counterintuitive truths of quantum fields, asking if the ghostly whispers of the Casimir effect could ever be amplified into a cosmic shout. By studying the impossible, we are conducting a stress test on reality itself. We are asking the universe the hardest questions we can devise, not because we expect a practical answer, but because the way it says no teaches us more than 1,000 easy yeses. The struggle to make the cylinder logically consistent led directly to deep insights like the self-consistency principle and forced a serious engagement with Hawking's chronology protection. These are not side notes, they are fundamental advances in our understanding of causality and quantum mechanics, sparked by a wild idea about spinning metal. History is littered with such fruitful impossibilities. For centuries, philosophers and mathematicians pondered non-Euclidean geometry, systems where parallel lines could meet or diverge. It was seen as a beautiful, abstract game with no connection to the real world. Then, Einstein needed precisely that mathematics to describe a universe where gravity is curvature. The impossible geometry became the true map of reality. The concept of atoms was philosophical speculation for millennia before technology caught up and revealed them. The laser was once derided as a solution looking for a problem. Each of these ideas stretched the imagination of its time, challenging hidden assumptions about what was possible. They expanded the territory of the plausible. The Tipler cylinder sits in that same lineage. It is a thought experiment that stretches the fabric of our theories until it groans, and in that groaning we hear the shape of truths we have not yet formulated. It inspires new mathematics, new questions about quantum gravity, and a deeper humility about the difference between what our equations allow and what the universe permits. To dismiss it is to stop asking questions. To engage with it, to truly wrestle with its implications, is to participate in the oldest and most vital human project, not building machines, but mapping the infinite and mysterious landscape of what is real. Yet the cylinder's ultimate lesson may be that general relativity is only half the story. To truly understand the fate of time, we must look beyond Einstein's elegant geometry to the chaotic, probabilistic realm of the quantum world. The grand, unified theory that merges these two titans, a theory of quantum gravity, remains the holy grail of modern physics. It is within this yet unwritten framework that the true feasibility of time travel, if any, will be decided. Two leading contenders offer starkly different visions of this future physics. String theory proposes that the fundamental building blocks of reality are not point particles, but unimaginably tiny, vibrating strings. In this model, the fabric of spacetime itself emerges from the collective dance of these strings. Closed time-like curves might be seen not as geometric whirlpools, but as specific vibrational patterns or configurations of these fundamental threads. The extra dimension string theory requires could provide new pathways or loopholes for temporal loops, ways to navigate time that are invisible in our familiar four-dimensional view. Conversely, loop quantum gravity takes a more radical approach. It suggests that space itself is not smooth and continuous, but woven from a network of discrete, finite loops, a kind of quantum fabric with the smallest possible stitch. In this pixelated universe, the concept of an infinitely long, perfectly smooth cylinder becomes meaningless. There is no continuum to twist in such a perfect way. Time itself might be quantized, flowing in tiny, indivisible ticks. A time machine here would not bend a smooth river, but would need to jump the universe's clock from one quantum state to a previous one, a process governed by probabilities and leaps rather than smooth geometry. Both theories, and others like them, are attempts to answer the very questions the Tipler cylinder raises. What happens when the smooth spacetime of general relativity is examined under the quantum microscope? Does it dissolve into foam? Does it reveal hidden dimensions? The violent feedback of vacuum fluctuations around a closed timelike curve is a screaming signal that our current theories are incomplete. Quantum gravity is the promised resolution, the rulebook that will tell us whether nature's censor, as Hawking suspected, permanently redacts the chapter on time travel, or whether it merely requires a more sophisticated, quantum-safe syntax to write it. This suggests a profound possibility. If time travel to the past is ever achievable, it will likely not look like a monstrous spinning rod of compressed stardust. Its mechanism will be something we can barely envision today, a technology born from a physics that seamlessly blends the very large and the very small. It might involve manipulating the quantum foam at the Planck scale, or tuning the vibrations of hidden dimensions, or harnessing the entanglement of particles across eons. It would be a process as far removed from the Tipler cylinder as a nuclear reactor is from a campfire. Both release energy, but through fundamentally different understandings of reality. The cylinder, then, stands as a magnificent monument to the limits of classical gravity. It shows us how far we can go with the mathematics of curvature and motion alone, and where that path ultimately ends at the shore of a quantum sea we are only beginning to chart. Our journey to yesterday, if it ever begins, will not start with a construction project. It will start with a revelation, a new equation that finally makes peace between the warring kings of physics and shows us a door in the universe we never knew was there. So where would your journey begin? the quiet streets of ancient Athens to hear Socrates debate, or the bustling ports of the Renaissance to watch a genius sketch a flying machine? Would you witness a pivotal moment you have only read about, or seek out a quiet, ordinary day in a lost world, just to feel the sunlight of a different century? This is not a casual question. Your destination reveals your deepest curiosity, whether it is for grand history or intimate human truth, and with that choice comes a weight. The biggest paradox that haunts these ideas is not just a logic puzzle for physicists, it is a personal one. If you could go back and offer a single piece of advice to your younger self, a warning or an encouragement, would you do it? The fear is not just of creating a temporal contradiction, but of erasing the person you have become. That struggle, the pain that forged your strength, the mistake that taught you wisdom, if you removed those stones, would the arch of your life still stand? Your answer tells a story about memory, regret, and the fragile beauty of a lived experience. So I am turning this over to you. Share your thoughts in the comments below. Tell us your first destination and the paradox that gives you pause. This conversation moves from theory to a shared exploration, because the most fascinating machine is not one made of infinite cylinders, but the human imagination contemplating its own timeline. The blueprint for a time machine is not locked away in some secret vault. It lives right here in the power of a simple thought experiment. Let us sketch our own, more plausible version of the Tipler cylinder. Instead of an impossible infinite rod, imagine a finite one, built by a civilization so advanced they have mastered quantum gravity and exotic matter. This is our sandbox. What would you design? Your first decision is not about power, but about safety. A single, unguarded time loop is a loaded weapon left in the street. So, what safeguards would you engineer into the system? Perhaps a strict observational protocol. The machine could be designed not for physical travel, but for remote viewing, projecting a non-interactive quantum sensor into the past, a ghost in the historical machine that cannot touch or be touched. Maybe you would install a cosmic version of the 3 laws of robotics, hard-coded into the machine's fundamental operations. First, do not create a paradox. Second, minimize interaction with the timeline. Third, if a paradox is detected, the system automatically shuts down and severs the loop. The machine itself could be the ultimate historian, programmed to only allow journeys to pre-approved, vetted coordinates, moments so vast and chaotic that a single, silent observer would be lost in the statistical noise, like watching a single raindrop fall into a stormy ocean. Your design choices reflect your philosophy. Do you trust a consistency-enforcing universe, or do you build walls against the possibility of branching worlds? With the safety protocols hypothetically in place, the next choice is deeply personal. You have one ticket for a purely observational trip. No speaking, no touching, no leaving anything behind. Which historical moment would you choose to witness, not to change but simply to know? Would it be a monumental public event, standing on a hillside to hear the real, unamplified voice of Martin Luther King Jr., delivering his dream, feeling the collective hope of the crowd wash over you? Or would it be a quiet, private moment of creation, peering over the shoulder of a scribe in a medieval monastery as they illuminate a manuscript by candlelight, each stroke of gold leaf an act of devotion against the darkness? Perhaps you would choose a scientific mystery, floating a sensor above the Tunguska forest in 1908, moments before the mysterious explosion, to finally see what truly arrived from the heavens. Your choice reveals what you value most, the roar of the crowd or the whisper of the individual, the solved mystery or the preserved beauty. This exercise does more than entertain. It makes the abstract weight of time travel concrete. You are not just listing features, you are confronting the responsibility. Designing the safeguards forces you to articulate what you fear most about this power. Choosing your observation point forces you to define what knowledge is worth the risk. The infinite cylinder may be fantasy, but these questions are real. They are questions about our relationship with history, our hunger for truth, and the ethical boundaries of curiosity itself. In designing your machine, you are not just playing with physics. You are deciding what kind of time traveler you would choose to be. The final verdict on this infinite spindle is a study in contrasts. With our current technology and understanding, the Tipler cylinder is undeniably science fiction. Its requirements are not merely difficult, they are laughably impossible. We cannot gather the mass of dead suns, we cannot forge a rod of infinite length, we cannot conjure stable exotic matter by the cubic light year. These are not engineering challenges waiting for a bigger budget. They are fundamental violations of the physical and logical constraints that seem to govern our finite, causal universe. As a blueprint for a machine, it is a non-starter, a castle drawn on paper that dissolves when you try to build its foundation in reality. Yet, to dismiss it entirely is to miss its profound and haunting significance. The cylinder is possible within the known laws of physics as we currently understand them. That is the crucial, mind-bending distinction. Its mathematics are sound, a valid solution to Albert Einstein's field equations. No known law of general relativity explicitly forbids it. This places it in a unique category, far removed from pure fantasy like magic or perpetual motion. It is a ghost in the machine of our best theory of gravity, a shape that the math permits even as the universe likely prohibits it. This tension is what makes the concept so fascinating and enduring. It is not a story about what we can build. It is a story about the outer edges of our comprehension, a lighthouse shining on the boundary between the possible and the plausible. The cylinder forces us to ask where that boundary truly lies, and whether our future discoveries might one day redraw the map entirely, transforming today's fiction into tomorrow's distant, shimmering fact. From a spinning cylinder of infinite length to the quantum roar that may protect causality itself, this journey reveals a universe far stranger than fiction. We began with a simple, if extreme, shape permitted by Einstein's equations, a cosmic drill bit twisting spacetime into loops. We followed its logic through the need for impossible materials and the terrifying feedback of vacuum fluctuations, arriving at the edge of known physics, where general relativity and quantum mechanics wage a silent war over the nature of time. The Tipler cylinder may never be built. Its infinite length is a logical ghost, and the exotic matter to stabilize it remains a phantom in our equations. Yet its true value was never as a construction manual. It serves as a profound philosophical tool, a stress test for our deepest theories. By daring to imagine the impossible, we are forced to confront the non-intuitive, counterintuitive bedrock of reality. We learn that time may not be a river but a geometry, that empty space seethes with potential, and that the universe might possess its own cosmic sensor to guard against paradox. This thought experiment, born from pure mathematics, expands our imagination and sharpens our questions. It reminds us that the frontier of human knowledge is not just in distant galaxies, but in the elegant, often bizarre, implications of the equations we write here on Earth. Our curiosity is the most powerful engine we possess, propelling us to map the boundaries of the possible and to dream of what lies beyond. If you enjoyed this exploration of time, physics, and the limits of reality, please like this video and subscribe to the channel. The journey continues in the comments below, where your thoughts on destinations and paradoxes become part of the conversation. Where should our curiosity turn next?